Welcome to part 12 of this video lecture series on the Hidden Markov Model. In this final lecture, we're going to cover what's called the Baum-Welch algorithm, the third of the key problems for hidden Markov models. Our example so far has been drawn from a toy problem of a robot moving through an apartment. And the technology and the algorithms that I'm describing are drawn primarily from a paper by Rabiner et al., whose citation is listed below. In our example, our robot is moving through an apartment and can have one of about 50 different states that it can be in, and those states are positions within the apartment. As it moves around, it has restrictions on which state can go to which state because of geographic proximity and walls that are preventing state transitions. And the robot, because it's inside, doesn't have access to GPS, and so it figures out where it is or tries to reason about where it is based on observing the floor coverings beneath it with the camera. By correlating those floor coverings with different state locations, it can come up with an estimate of where it is. And we formalize that as a hidden Markov model, a mathematical representation of a kind of inference game that consists of 5 different parameters. N, which is the number of states that the robot can be in, or that the hidden Markov model can be in. In this case, each state corresponds to one of the positions within the apartment. M, which is the number of different observations that the robot can make in one given time step. In this case, we're looking at 7 different floor colorings that the robot can observe. A is a 2-dimensional matrix, in principle, of transition probabilities, the probability of moving from one state I to another state J. Every time step, the robot must move from one state to another, even if that transition means staying in place. B is a vector of probabilities of seeing the different observations given that you're in a particular state. And you can imagine that this is going to vary over the course of the apartment. If you're over a wooden floor, you're much more likely to see a wooden floor beneath. If you're in an area that has wooden floor, you're going to see a wooden floor. But if you're in an area that has maybe a stone floor, you're going to see a stone floor. If you're in an area that has carpet and a wood floor, you maybe have a 50-50 chance of seeing each. So B is a variable that captures the probability of seeing the different floor colorings depending on what state you're in. And finally, pi is a variable that captures what the probability is of starting in a particular state and then moving through the world and making your observations. Our observations consist of observations from time 1 to time capital T, each one on a given time step, some kind of a beat, some kind of a measurement that's made periodically and regularly. And so the different components of our HMM for this robot world are shown below. The states, the observations, the transition probabilities, and then the observation probabilities. Previous lectures, we've looked at the 3 key problems for HMMs, trying to figure out what is the probability that a given model that we already know, the model consisting of A, B, and pi, those are the the different probabilities, and we wrap those up into a variable called lambda. So first question is, what's the probability, given lambda, of seeing some observations? And we showed how to solve that using the forward-backward algorithm. The next key problem was to try and understand what sequence of states best explains a sequence of observations. So if you see different floor colorings in a particular pattern, particular temporal sequence, what is the most likely sequence of states that you went through in order to observe that? Or in this case, what path did the robot traverse in order to see that particular set of observations? This algorithm, the algorithm that we demonstrated to solve this we demonstrated 2 algorithms to solve this. One was a state-by-state algorithm in which we calculated the gamma parameter, but the more helpful way to solve this was through the Viterbi algorithm, which tries to find the most likely sequences of states that would generate observations where those states have to be accessible from one to another. So that was a Viterbi algorithm. In today's video, what I want to do is I want to look at the third problem. The third problem is, given a set of observations, how do we learn the probabilities of lambda to maximize the likelihood of generating that sequence of observations? This is the learning problem associated with the hidden Markov model. And while problem number 2 is probably the problem that is executed the most often because we're trying to recover some sequence of patterns the robot went through, etc., 3 is definitely the most difficult and one that's necessary in order to get the model to use for 1 and 2, if we're going to learn the model. So that is the introduction for the Baum-Welch algorithm. The Baum-Welch algorithm is a extension of the things that we've learned so far in order to support learning our model lambda. So the rest of the lecture, we're going to walk through how the Baum-Welch algorithm works. So to start with, let's review what resources we've developed, what mathematical formalisms and which algorithms we've tackled in order to use these in order to make our estimates better. First of all, recall that we have a variable called alpha. Alpha is different than A. Remember, A is our transition probability from one state to another, but alpha is different. Alpha captures the probability that we're in a given state, Si, at time lowercase t, given all the observations that have come before. And so what alpha tries to capture is not the exact path by which we got to state Si, but the probability of getting to state Si at all, given the observations that came before. Regardless of what pattern, regardless of how we got there could be multiple paths that got us there. Overall, what is the probability that we would end up in state Si, given our sequence of observations up to a given time? And so alpha is called our forward parameter because we're moving forward through time, considering what came before us in terms of observations and coming up with a probability of being in a particular state. So to clarify that, visually, what that means is you've got your robot going through time, making some observations, that's that blue arrow there. And given that sequence of observations, what alpha t answers is, what is the probability that we're in this particular state given the sequence of observations we've seen so far? That's the forward parameter. Now, the next resource that we have available to us is the backward parameter, or beta. Again, beta is different than B. B is our observation distribution, but beta captures the probability that we would be in a given state Si, knowing what's going to come forward and what's going to come in the future, but not knowing what came in the past. So it's kind of the it's a mirror image of the alpha parameter, more or less. There's a slight difference in when we account for the observation probability between the two. But basically, it's the mirror image of beta. So beta says, we're in state Si now. What's the probability of being in Si given the sequence of observations we're going to see in the future? So visually, it looks like this. A robot is in a particular stream of observations. We know what's going to come. So what's the probability that the robot is here knowing what's coming next in the future? Of course, this isn't something that you can do real time. This would have to be something that you infer about after you've already collected the data. So that's alpha, our forward parameter, beta, our backward parameter. And then finally, in our discussion of the Viterbi algorithm, we also generated the gamma parameter. Now, the gamma parameter is like a fusion of the alpha and the beta parameter. It answers the question, what is the probability that at time lowercase t, we're going to be in state Si, knowing everything that came before and knowing everything that's coming after? We were able to develop the answer to the gamma parameter by using the answers to the alpha and the beta parameters, because we're able to take the alpha parameter for a particular time and state and merge it, multiply it, times the beta parameter for a particular time and state. And then after normalizing it, that gives us the probability of being in one state, regardless of all the possible ways we could have gotten there, and regardless of all the possible ways that we could continue going afterwards. It's sort of like a bow tie where we're coming down to the middle and anchoring and clamping our question down to one particular state, even though we know that there are observations before and after that. So that is combining those two things. We are in the middle of a sequence of observations, and we want to know, given where we came from and where we're going, what is the probability of being in a particular state? Now, you can imagine that these are different, because you can imagine that if you only knew what came before, you might guess that you were in one place in the apartment. But if you know also what's coming in the future, you might have to revise that guess because maybe those future observations make the most likely current position impossible to actually be at. And so each one of these different parameters adds additional information to our ability to reason about where our robot currently is. So our resources then that we have to solve our third key HMM problem are our alpha ti parameter, our beta ti parameter, and our gamma ti parameter. The Baum-Welch algorithm solves for a local minimum. There's no known way to solve for the globally optimal parameters of lambda. This is the best that we know how to do is to search for a local optimal or a local result. We do know that the Baum-Welch algorithm is going to converge to a stable good answer, but it isn't guaranteed to be the best answer. And this is because this is a common problem with trying to do different algorithms that find your local minimum. So this graph here kind of represents what we're talking about. If this ball represents the current parameters of lambda, and we want to optimize the parameters of lambda, we're going to gradually make them better until we get the best possible probability for our observations given our model. But even though we are at a good point, we're at a local maximum in this case, if we had started our model somewhere else, we might have achieved a higher maximum, or in this case, the diagram shows a global optimal. Since we don't know where on this red curve we're starting, we don't know which one of those peaks we're going to end up at. All we know is that there is a peak, and we can get to that peak given our current model. That's some work that's proven by some work that we're not discussing in this algorithm, but was originally done by Baum, a Baum-Welch algorithm. Okay, so what this means is that what we're doing is an algorithm that's called an expectation maximization algorithm. This is an iterative algorithm, and it converges to a local optimum. So we have to run this several times in order to get our best answer. It is also sometimes called a gradient descent algorithm. And I put descent in quotes because depending on whether you think you're going up or down, you're either finding a local maximum or a local minimum. In any event, we're going to find a peak, or if you flip the parameters, a valley. We're trying to follow the curve till we get to an extrema. All right, knowing that, we now need to introduce a new mathematical tool. And we're going to introduce the variable xi, right? Okay, I had to check with my my son, who's learning Greek right now, to know how to pronounce this variable. So xi, it kind of looks like Dr. Seuss. So xi t I j. This is going to be a variable that captures the probability that at time lowercase t we're going to be in si, and at time t plus 1 we're going to be in sj, given our set of observations and our lambda. So now this shouldn't look really different than the other parameters that we've had, but what you should notice is that she is capturing two different states and asserting that we want to know not just that we're in state Si or state Sj, but what's the probability of being in one and then transitioning to the other, given our observations and our model. All right, well, how can we calculate this? We're going to need to flesh this out a little bit in order to figure out the answer to that. Visually, if you need a visualization for it, this is a visualization that tries to capture xi. So what we've got here is we've got all the states that we could possibly be in lined up in the left column. Those are all 53 states that we could be in terms of being in one of the positions. And regardless of how we could possibly get there, what she's capturing is the fact that we're going to end up in Si. What's the probability that given our observations, we're going to end up in Si, we're going to transition to Sj, and then we're going to see the remainder of the observations that we have, regardless of what states we transition through in the future. Kind of a bow tie again. Now we can leverage these resources that we have in order to figure this out. And if you'll recall, alpha t sub I is capturing the left half of this quantity, and beta t plus 1j is capturing the right half after the transition of this quantity. So we've also got that little piece in the middle that we've got to deal with. The way that we get from Si to Sj in terms of the probabilities is we take our alpha t sub I, we multiply it times the probability of moving from I to j, that's Aij, and then we multiply it times the probability of seeing our observation at time t plus 1, given that we're now in state j, and then we multiply it times our beta parameter to fill out the rest of the trajectory along the way. So in this way, we've sort of created a point in time, a particular state, another point in time, a particular state. We've looked at everything before it, we've looked at everything that's going to come after it, and we've connected the pieces together. The way that we can calculate this then is to just formalize those different parameters. We say xi t ij is alpha t sub I, getting us to state I, Aij, the probability of moving from I to j, Bj ot plus 1, the probability of seeing our observation at time t plus 1, given that we're now in state j, times beta t plus 1j, the probability of being in state J given everything that's coming in the future. And then we have to divide it by a normalizing factor to account for the fact that we're trying to calculate a probability, not a likelihood. How do we calculate that denominator? Well, it's kind of straightforward because all we do is we iterate over all the possible i's and j's. So we're interested in what is the probability of moving from one I to one j at a given time. So what we do is we find out, well, what's the sum of all the probabilities of all i's and all j's at that given time? And so we do two loops, a loop over j and a loop over I. We add up all the possible, basically all the possible xt's in the denominator, and that guarantees that this is going to be a probability by dividing it by that normalizing factor, rather than just a likelihood by looking at the numerator. We know alpha t, we know aij, we know bj, we know beta. We have all those quantities, and so now we can actually calculate xt. If you want to relate this to our other quantities, there is a clear relationship between our new variable xi and gamma that we already had calculated before. Gamma is just one point in time, and so if we sum up all the possible destinations of being at I and going to j, and we sum up over all possible j's, well, that therefore must be gamma t sub I, because we're basically marginalizing out the destination variable from xi. All right, so that's helpful to understand what we're looking at here, and that it's understanding that will help resolve our learning algorithm. To compare the two, on the left side we've got gamma t visually. You can see it's our entire observation sequence, and then we're asking what is the probability of being in one state at time t, state I, and then we can derive that by looking at xi t and saying, well, if we know all the si, sj parameters and we just add up all the possible sj's, that's going to give us the total sum of being in si. So we can move from the visually from the right side to the left side by doing the summation. All right, so gamma t sub I is the probability of being in state si at time t. We're now going to think about the fact that if we sum over all time observations, since gamma t is one moment in time, the probability of being in si at one moment in time, and we want to say, given all of our observations, what's the probability of ever being in state si? Not just at time t, but during our entire observation sequence, what's the probability of ever being in state si? We can figure this out by summing over all of the over all time periods the variable gamma ti. If we sum over all t, then we have a number that can be treated as the expected number of times that si is ever visited. All right, that's going to be helpful because we have a guess of how many times we're going to be in si. Well, xi t ij is the probability of transitioning from si to sj at time t. So what if we wanted to ask, what's the probability of ever transitioning from I to j, regardless of the time? We can do the same thing. We can sum over all time steps this xi t parameter, and then that gives us the likelihood, a number that we can treat as the expected number of transitions from si to sj that we're ever going to see at any time period, given the data that we've got so far. All right, so we're kind of like, we're doing a sum over time so that we can not think about the difference between the different moments in time when we're going to be at particular states. So, to formalize that, if we sum over all times t1 to t minus, from lowercase t equals 1, all the way up to lowercase t equals capital T minus 1, so going almost the entire string of observations, then gamma ti becomes the expected number of transitions from state I. How many times are we in state I and moving out of it? And then xi t, summed over the same parameters, same range, is the expected number of times we transition from si to a specific sj. These are helpful quantities for us. Where are we then? We have an existing model lambda consisting of the probabilities that we would like to adjust, a, b, and pi. We have a set of observations that came from running our robot through the world. This is our training data, O. We now have the ability to calculate a set of tools, a set of mathematical tools to help us improve our estimate. We have alpha t, beta t, forward and backward, gamma t, Viterbi algorithm, and then xi t, something that we need for Baum-Welch. How are we going to use these in order to improve our model? How are we going to calculate lambda bar such that it is an improvement over lambda? Well, lambda consists of three different parameters, pi, a, and b. So let's look at each of them in turn and how we can optimize our estimate to improve it. How do we improve our estimate? So for starters, bar pi is simply gamma 1 of I. So we can say the expected frequency of being in state I at time 1 is just gamma 1 of I. So pi, going through all the different i's, pi I, there should probably be a subscript on that pi. All of the different pi parameters can be updated by looking at our gamma 1i parameter. That one's kind of straightforward. Remember, gamma I was calculated from the previous model and the observations that we saw. All right, now we want to update our transition probabilities, and we'll call them bar A, ij. Well, we can calculate a new update of our transition probabilities by saying, what is the expected number of transitions from state I to state j divided by the expected number of transitions from Si? That'll give us a probability of moving from I to j. What's the number of transitions from I to j, and how many times do we expect to be in I? We have the ability to calculate that. We can calculate that by summing over all time steps 1 to capital T minus 1 of xi t, that's the transition from I to j, and then dividing that by the sum over the same range of times of gamma ti. This gives us an improved estimate of that we're calling bar A ij. Now remember, our parameters xi and gamma were both calculated from what? They were calculated from our previous lambda and our set of observations. So our previous lambda and our set of observations now are combining to give us a better estimate for our transition probability. Transition probabilities, bar A ij. Finally, we need to update our observation probabilities. Our new observation probabilities, bar jk, is going to be the number of times we are in state j and observing the particular symbol we care about, vk, divided by the expected number of times we're in state j at all. Just the probability of seeing vk given we're in state j. We have the ability to calculate this. So in the numerator, what we're going to do is we're going to sum up all the times that we expect to be in state j, but we're only going to sum up those times when we saw the particular observation that we're interested in. So all the different times that we saw that we're in the state, what's the expectation of the number of times we're in state j and seeing vk? We do that by summing from 1 to capital T. And then we divide over all the times that we were actually in that state, regardless of what we observed. And in this way, our gamma t and our observations, based on our lambda, our gamma t, and our observations, we're able to come up with a new estimate for our observation distribution, bar b, based on those previous parameters. Well, those are the three things we need. We need a new pi, we need a new a, and we need a new b in order to create a new lambda. So together, all three of those things give us a new bar lambda. So just to summarize, given lambda, which consists of a, b, and pi and o, that's enough that we can efficiently produce alpha t, beta t, gamma t, xi t. And given those new parameters that we got, alpha t, beta t, gamma t, and xi t, as I just described, we can produce a new lambda, bar lambda, consisting of bar a, bar b, and bar pi. Well, this then gives us an iterative procedure we can follow. We take our model, we calculate our mathematical aggregates. We take our aggregates and we produce a better model. We produce new aggregates, then we produce a better model. New aggregates, better model. This iteratively is guaranteed to converge on a local optima. And this is the process that is called expectation maximization. When we go from our model to our variables, we call that re-estimating our parameters, and then we take our parameters and we maximize the expectation of those parameters. We maximize the expectation of our model by recalculating our model. And then we re-estimate our parameters, and then we maximize our expectation, and then we re-estimate our parameters. And eventually, the changes between our iterative models will be small enough that we'll say there's effectively no change and we're done converging. And then we'll use that model as our now trained model on the data that we've got. So that was the third problem. There were three key problems that we were tackling. The problem of seeing what's the likelihood, no, what's the probability that we would see some observations given a model. What's the best set of states that explains a sequence of observations? And finally, how do we tune our model? How do we learn our model given a set of observations that we have to maximize the likelihood that our model would generate those observations? We've tackled all three of those problems. They're difficult, timely, very interesting problems. I think it's very clean. I really like these mathematical formulas because they feel like they're accessible and they're clean and they lend themselves to a straightforward algorithmic implementation. So thank you for watching. Our robot toy house cleaner finder roamer is happy that you were able to walk through these problems with us as well. If you have any more questions about this or would like to read more, I would refer you to that original paper, which has a lot of this content and also goes on to discuss other issues around the application of hidden Markov models to speech recognition. Thank you very much for your attention.
I will pronounce my Greek letters correctly. Xi.